Okay, hello everybody. I hope you're all safe and well. In this video, I will be going over quiz 8 that was due in week 5, due today, on equilibrium. So our first question says, assume that the following reaction is at equilibrium at 100 degrees Celsius. Methane combines with water in the gaseous state to form hydrogen gas and carbon monoxide. It has a delta H value of 131.3 kilojoules, and that's a positive delta H value, which tells us that this is an endothermic reaction because we have a positive value for Q. So since we're looking at the equilibrium concentrations and expression here, we're going to want to think about where heat's going to lie on the equilibrium scale here. So since it's endothermic, heat's going to lie on the left. It's going to be considered a reactant. So for the sake of visualization and being able to understand this concept, I'm going to put heat there for us to understand that. So if heat was negative and it was exothermic rather, I would put heat on the product side. So the question says, which of the following changes will cause the reaction to shift to the right? So this is an example of asking us to apply Le Chatelier's principle. And we did talk about this, it's very important. Le Chatelier's principle just discusses how different shifts that affect equilibrium will cause a reaction to shift a certain way in order to achieve equilibrium once again. So which of the following changes will cause a shift to the right in order to achieve equilibrium? So decreasing the volume of the container. Well, let's think about it. If we decrease the volume of the container, we're going to want to go to the side with less moles, and that would be to the left. So that's not going to be the answer here. Increasing the pressure is the same thing as decreasing the volume. They're inversely related. So that's not going to be it. If we decrease the methane concentration, well, we're going to want to raise the methane concentration. So we're going to want to shift to the left. So that's not it. If we increase the carbon monoxide concentration, we're going to have too much product and we're going to want to shift to the left. So that's not it. So it looks like our answer is E here by process of elimination, but let's understand why. Increasing the temperature, yes, that makes sense. If I increase the temperature, I'm going to have too much heat on the left-hand side, on the reactant side, such as an endothermic reaction, and I'm going to want to shift to the right
It's
in
1
order,
o'clock.
my apologies, in order to get more heat on the right-hand side. So if I increase the temperature in an endothermic reaction, I'm going to shift to the right. So that's why the answer here is E. Once again, I'll clarify that. Since it's an endothermic reaction, heat is a reactant. If we increase the temperature, we're going to have too much heat on the reactant side, and we're going to want to shift to the product side in order to achieve equilibrium. The next question says that if the value of Q, the reaction quotient, is greater than K for an equilibrium reaction, then, okay, so this is just comparing Q to K. So there's some rules for Q and K. So we have to see which of the following is true. So if Q is less than K, the reaction is going to proceed to the right. And if Q is greater than K, wow, that's a G, my apologies. If Q is greater than K, the reaction is going to want to proceed to the left. And if Q is equal to K, we're at equilibrium. So those are those rules that were discussed in the lecture. So the question says if the value of Q is greater than K for an equilibrium reaction, then we're going to want to proceed to the left. So the answer here would be C. Okay, So these are just some things you need to memorize to understand. So number 3 says that calculate the equilibrium constant K for the following reaction given the following equilibrium concentrations at 500 degrees Celsius. So it's the decomposition of sulfur trioxide into sulfur dioxide and oxygen gas. We're given the equilibrium concentrations and we want to know the equilibrium constant K. So the equilibrium constant K can be written as a ratio, and it's products over reactants. So our products here are sulfur dioxide. Now you got to be careful with the coefficients here. We have 2 sulfur dioxide, so this quantity is going to be squared. And we have oxygen gas, and that's going to be divided by our reactants, which is sulfur trioxide, but we also have 2 of those as well. So that's going to be squared. So when we just have to write this as a fraction here, we would take the value for SO2, which is 0.35, and we would square that, multiply that by the value for oxygen, which is 0.44, and divide that by the value for sulfur trioxide squared, and that's 0.52 squared. So we get that K is going to equal, let's see here on my calculator, 0.1999, repeating, or we could just say, if we round, 0.2. So the answer here would be D. Okay, number 4 is just a little bit of a reversed flip of what we just did. The equilibrium constant K for the following reaction is given, and it's 1.0 times 10 to the negative fifth at 1500 degrees Kelvin. And we see that the reaction is nitrogen and oxygen gas form nitrogen monoxide. If 0.75 molar nitrogen gas and 0.75 molar oxygen gas are allowed to equilibrate or reach equilibrium at 1500 K, what's the concentration of NO, meaning at the equilibrium concentration? So all we're going to do is write our K expression, and we're going to manipulate that algebraically to solve for the concentration of NO. Now, a couple of things here that you need to be aware of is that we have to keep in mind that the concentration of NO is going to be squared, right? Because we have 2 right here. So we're going to technically have a x squared value, which means we're going to be dealing with a square root, which is not uncommon with equilibrium. But you just need to be careful with the math that you don't make any algebraic mistakes. So let's first write the standard equilibrium expression. So K is going to equal the concentration of nitrogen monoxide squared divided by nitrogen gas times oxygen gas. Now, another neat thing to notice here is that the concentrations of nitrogen gas and oxygen gas are the same. So I could rewrite this, if I want to include the math, as, the numbers rather, as the K value, 1.0 times 10 to the negative fifth, equals the concentration of NO squared divided by 0.750 squared. Now the reason why I wrote 0.750 squared is the concentration of nitrogen and oxygen gas are the same, so the quantity is the same. So if I could write 0.75 times 0.75, and you're just multiplying them, or to save a step, you could just write squared. So now we're solving for the concentration of nitrogen monoxide. Now, you could, if it helps you to solve this like an equation, you could put this value as x. Some people like to do that. I prefer to keep it as nitrogen monoxide or as the chemical formula because we are in chemistry class, and it is a good habit to get accustomed to being able to work with um, um, chemical formulas as variables. Sometimes it's a good habit, so I would like to teach you to do that as well. So now we're going to solve for the concentration of nitrogen monoxide. So to do that, I'm going to do 1.5 times 10 to the negative fifth times 0.75 squared, and that's going to equal the concentration of nitrogen monoxide squared. So I can get a value for this. Remember, I always tell you when you can get numbers. I can get a value for this. And when I type this in on my calculator, I get 5.625 times 10 to the negative 6, and that equals my concentration of nitrogen monoxide squared. Now, only problem here is that we have that squared value. So in order to undo a square, we need to take the square root of both sides. So I'm going to take the square root of 5.625 times 10 to the negative 6. So I get that the concentration of nitrogen monoxide at equilibrium equals 2.4 times 10 to the negative third molar. So our answer here would be A. So this is a pretty good example of the kind of equilibrium questions you'll see. This is probably a little bit easier than what you would see on a test, but you just got to be careful with the algebra. Don't make those silly algebra mistakes. And finally, we have our question 5, which was probably the question everybody mostly got wrong. So that's I'd like to go over that. At 1500 K, the oxidation of sulfur dioxide produces sulfur trioxide. So we just reverse the reaction above. With an equilibrium constant of 2.3 times 10 to the fourth, a quantity of sulfur dioxide and oxygen were placed in a 1-liter flask and allowed to react at 999 degrees Kelvin. After an hour, the flask contents were analyzed and the following was obtained. So at 999 degrees Kelvin, we obtained the following measures. And we want to know which of the following is correct. Now there is a problem here. And the problem is that at 1500 K, we obtained the following equilibrium constant. I told you that at a different temperature, I obtained these results. These results are null and void for us. If it is not at the same temperature at which the equilibrium constant was obtained, we cannot use these numbers. That's why we always have to pay attention to our temperature values to make sure that they are in line with the K value. So unfortunately, a lot of people didn't pick up on this, and the reason why I put this question is it's a key concept to understand, that the K value must be measured at the same temperature or as the concentrations were measured at. So if I measured these concentrations at 999 degrees Kelvin, but my equilibrium constant was measured at a different temperature, I can't compare these values. It just doesn't work because they're at different temperatures. It doesn't work mathematically, and conceptually that should make sense to you. I'll repeat it again just to make sure it's clear. If I measure my equilibrium constant at 1500 K and measure my concentrations at a different temperature, I cannot use my equilibrium constant to compare these concentrations and make a statement regarding the equilibrium because they were at different temperatures. So all of these statements, A through D, are null and void because this is not a valid question because it was at a different temperature. So the answer here would be none of the above were true. So a small fraction of you did pick up on this, which I was happy about, but it's always important to make sure you read the question. A lot of times students think that those temperatures that we throw in at the beginning of the problem are just there, just standard, to let you know just that's just how the problem is written, but not always. You need to just pay attention. So I hope this helped you to understand Quiz 8 equilibrium. Please email me if you have any questions. Thank you.